Alright, so welcome to today's video on algebraic fractions. We are focusing on these three objectives, the first of which is being able to recognize algebraic expressions containing algebraic fractions. We want to learn how to simplify these statements because we're going to be dealing with equations that involve algebraic fractions. So we need to learn how to simplify them first of all, so we'll know how to work with them when we see them in equations. And then lastly, one of the things that helps us see how some of the things we do relate to our world is to show it in a real life scenario. So let's get straight into that. So I want you to look at the image here. I want you to put yourself into the situation. You're eating a chocolate bar and I want you to think about something like a Twix or maybe a Goldfinger or Mars or something, and you know it have bars, right? That's a whole bar. And you just always have this scenario when you're eating something, somebody want piece, right? So if it's not your siblings, it's your friend, or it's some random person who just feel that they's your friend, they see you eating your chocolate bar and they want a piece. They're feeling a little generous, right? But you don't have any clear markings on it because it's not split into, little blocks. It's an actual bar, it's a whole bar. So you estimate where along that bar looks a little like halfway, and you say, all right, I'll be generous today, and you try to break the chocolate bar into two equal parts, right? So when you break an entire bar, I want you to remember that it's a whole bar, so something that looked like that. And when you broke it, you essentially gave them a part of it. And what do we know that we have used before is part of a whole. So if we remember, even from those elementary states in primary school, when we were now starting to interact with parts of a whole, we would have met the fractions. So we would have met some common fractions. And as I mentioned earlier, you just rough estimate where is half of this bar, right? Now, I want you to put it into perspective now. You don't know what is the length of the entire chocolate bar, right? So let's just say we refer to the length of the chocolate bar as x, right? The length of the chocolate bar is x. And because your rough estimate about halfway along the bar, we've divided that bar of length x into two equal parts, roughly. So it now becomes a fraction, right? So you took x over 2 for yourself and you gave x over 2 to whoever it was who wanted peace. And this here is what we call an algebraic fraction, right? So we're going to get into algebraic fractions. We're going to learn how to recognize algebraic fractions because they don't only come as nice and simple as this, unfortunately. And when you are able to recognize algebraic fractions, you know how to interact with these statements and how to work with them. So let's get straight into what algebraic fractions are, right? So I want you to think about the fact that with fractions, we're talking about a part of a whole. We've taken a whole object and we're attempting to divide it equally among a certain number of persons, as the case may be. So in our little scenario, we would divide in one chocolate bar of length x between two persons. So this means we're doing the operation of division, where we're taking a whole object and we're attempting to divide it equally between two persons. So this is what fractions are as a result of, attempting to take a whole and divide it into pieces to share among a group of people, right? Now, whenever we think about algebraic fractions, right, if you can remember the types of numbers you've interacted with, like I said, we're connecting it back to fractions, right? Because the word fraction is there. But we know that fractions is the set of whole of rational numbers, right? So we're talking about any number that is of the form p over q, right? Where basically p and q would come from whole numbers, and when we talk about this particular form for rational numbers, we have to remember that we cannot have a denominator of 0, right? So q cannot be equal to 0. So whenever we talk about rational numbers, we're talking about a whole number over a whole number, all right? That's what we're looking at. And this is our numerator part, this is our denominator part. So just like what we were talking about earlier with that scenario, right? If I want to know what an algebraic fraction is going to look like, it's going to be quite similar to this form, right? Where I'm going to have some numerator over some denominator. Now, because I'm dealing with algebraic fractions, what I'm going to see, I might have something like earlier, x over 2. And that's not the only way that you can get an algebraic fraction. You can also have algebraic fractions where your denominator is algebraic. So we could have something like 2 over x, right? If we had to, put that into a real life context, we're talking about we know what we want to share, but we are not sure how much we're going to be sharing it among. So that's where we have that unknown in our denominator. And of course, we've learned of different types of algebraic expressions. So we know that we're not just going to have a variable by itself. Sometimes we could have things like a variable with a coefficient. So we could have things like this. We could also have an entire algebraic expression where we have a variable, constant, and coefficient. So we could have something like this, right? So the idea behind it is just to be able to recognize that algebraic fractions are basically fractions that have some algebraic part to it, right? And I have to add it in. It's not going to only look like that, because eventually you're going to be working with algebraic statements that also could look a little like this. Right? You could also have things that look something like this. So the idea, like I was saying, is just for you to recognize that algebraic fractions will have a fraction form, and you will have a statement either in the numerator or denominator part that looks like an algebraic expression, right? Regardless of what that expression might look like, you just want to be able to recognize that there's an algebraic statement somewhere in that fraction, all right? So if you're keeping up so far, if you understand what an algebraic fraction looks like, we're going to get into the main objective, which would be to simplify algebraic expressions today, all right? So in dealing with algebraic fractions, we need to be familiar with certain concepts that we would have touched on in our journey as math students. So before you even want to deal with algebraic fractions, right? Most people already dislike fractions. So even if you dislike fractions, you need to make sure that you could work with it. So definitely, before you get into this lesson, if you're not very comfortable with things like finding LCM, you want to go back and look at videos on how to do your LCM and practice finding LCM, right? If you're good with LCM, but you're having trouble with fractions, we are dealing with algebraic fractions, so it means that you need to be familiar with operations and fractions. Then, in some of the simplification of algebraic fractions, as we go along, we're going to have to expand brackets. So you want to make sure that you're familiar with distributive law. You also want to be familiar with doing operations on integers, because once we start algebra, you're going to start seeing integers all over the place, and you want to make sure that you can add and subtract and divide and multiply with your integers quite comfortably, because you don't want to make a mistake with just integers to end up causing your entire solution to go haywire, right? And of course, the last thing is how to simplify algebraic expressions, because we're dealing with algebraic fractions, right? So we want to know, how do we treat with simplified algebraic expressions where we have like and unlike terms. So make sure that you can do all of these things before you proceed with doing the algebraic fractions, right? If you're comfortable, or if you just want to see what this looking like and then you'll know what you want to go address after, let's take a look at how we simplify this particular example that I have here. So we have the algebraic statement x minus 3 over 3 plus x plus 2 over 4. And what we're going to do now is simplify this statement, right? Always remember that you can only simplify expressions. We're not solving for x, although there's an x there, so don't get carried away when you start to see it gets easy. You just want to simplify it. So let's go on to doing the simplification. So I've outlined some steps which may or may not help some, but I want you to just pay attention to what you're doing at each step because it helps build your reasoning. When we have to simplify this statement, the first thing you want to do, you know that you're dealing with fractions, so you definitely want to take a look at your denominators. And in this case, when I look at my denominators, I want to take into consideration, are they the same or are they different? Just like with regular fractions, right? We know that when we're doing addition and subtraction of fractions, we usually have to look at those denominators. And if the denominators are the same, well, proceed ahead with adding or subtracting as the case may be. But if our denominators are different, what do we do? If our denominators are different, we always have to bring them to a common denominator, which means finding LCM. So you understand why I highlighted that LCM is important for you to know before you can proceed with this particular topic. Now, finding LCM might be easy for some and it might not be easy for some. So let's just take a look at how we find the LCM, just in case you need that to just brush up on to kind of catch the rest of it, right? So let's say you have, in this case, we have the denominators 3 and 4. We can list out multiples of 3 and 4 until we find a common one, so we can do it that way. So multiples of 3 would include 3, 6, 9, 12, 15, and we could keep going on, right? Well, I'll stop right there. And then my multiples of 4 would be 4, 8, and 12. I could keep going on as well, but I'll just stop off right here because I already see that they both have the multiple 12 in common. Alright? So this is a great way to find an LCM on your side working in case you need to do this, right? You can use your multiples as the case may be. And let's just say you can't recollect your timetables because I'm sure there are times when your brain is saying 3 by 2 is 9 and all kind of craziness has happened, right? So let's try doing the other method, which we usually refer to as the ladder method. This way you are doing division, right? And again, either way you take it, one of these methods uses an operation that you should be familiar with, right? So multiples means you're multiplying, so learn your timetables if that way might be easier for you and you can multiply easily. And in this case we're going to do division, right? Of course we know how to divide, but what I mean to say, sometimes we deal with other numbers, not just little 3 and 4 sometimes, okay? So here I could start with the prime numbers as factors of these, right? And it has to be a factor of either one. So I could start with 3, so we can say how many times can 3 go into 3? 1. And because 3 just can't divide 4 exactly, I am going to write it back, and then I'm going to have to consider a prime factor that can go into 4. And sure, yeah, you could just go straight ahead and put 4 here, but the reason why I use prime factors and why I would recommend that any student doing LCM like this, you use your prime factors, it avoids the repetition of any common factor for numbers that may have multiple common factors, right? So let's just use 2 and continuing on the side. 2 can't go into 1, so we're just going to write back the 1. And 2 will go into 4 2 times. And then we're going to do one more division by 2, because the objective with using this technique for LCM is to get the last row to be all ones. Then from there, what we'll do is take the product of all the factors that we've used in our ladder method, and this will give us our LCM. So our LCM here is 3 times 2 by 2, which will give us 12. Right? And you would notice it in particular if you're using larger numbers. If for some reason we decided to use 4 and 4 was a common factor to a couple of other numbers that we would probably find LCM of, you may encounter problems where your LCM does not end up being the LCM, right? Have you ever encountered a problem where you're trying to get the LCM, but instead of getting the LCM, you get a larger multiple versus the LCM? That's what happens when you don't really use your prime factors in cases where you have numbers that have multiple common factors. Alright, so use your prime factors. Now, once we understand how to get LCM, we now have the LCM. What do we do with it? Well, whenever we find an LCM, we're finding that to bring our fractions to a common denominator. So at our next step, we're going to express each of our fractions as equivalent fractions using our common denominator, right? And what that could look like is something like this. Now, with fractions, right, we're only dealing with numerical statements. So now with the algebraic ones, I want you to pay attention to what happens when we do this portion of expressing our algebraic fractions as equivalent fractions using our common denominator now. So the first thing we do, as always, just like with regular fractions, we're going to consider how many times our old denominators can go into our new one. So 3 into 12 is 4, and just like with fractions, you'll take that factor of 4 and you'll multiply it by the numerator of that fraction. So we're basically going to be multiplying x minus 3 by 4. Now, while some of us might be able to multiply it one time and you could write it there, that's perfectly fine, but I do recommend taking your time while it's still learning the process so you don't make mistakes, alright? And especially when integers are involved, you want to make sure you get your signs correct, so pay attention to little things like that. So I'm just going to write on the top here 4 times x minus 3. And then my operation here is addition, and then I'm going to consider how many times does my denominator 4 go into 12, and that will give me 3. And the same thing again, you're going to multiply the numerator. This time the numerator here is x plus 2. You're going to multiply that numerator by 3. So what we're going to write here should be 3 by x plus 2. So this is what it will look like. Alright, so we have our statement now as a fraction on one denominator, which is ideally the objective of simplifying algebraic fractions. But the simplify part means that we must not contain any brackets that need expanding, and we must not contain multiple terms with the same variables or multiple constants in the numerator. We want to simplify it as much as possible so we don't have multiple terms in our numerator. So what we're going to do now, we're going to expand the brackets, right? So our third and final step basically is to simplify, and simplify as much as possible. So this would mean doing things like expanding these brackets if we didn't already do that. And then if you've already simplified the brackets from before, all I want you to do is, if you remember things like and unlike terms in algebraic expressions, rearrange your statements and simplify the like and the unlike terms and see what you get. So let's expand the bracket for those of us who are still here. Let's expand the bracket. So in expanding the bracket, I have to recall my distributive law. And if you remember what distributive law is, you'll know that it tells you have to multiply what is outside of the bracket by what is inside of the bracket. So we're going to expand this now. So expanding, we'll get the first part, 4 by x will give me 4x. 4 by 3 will give me 12. And because I have a negative 3 here, I'm going to get a negative 12. Next, let's expand. 3 by x is going to give me 3x. And then 3 by 2 will give me 6, and because they're both positive, I still get a positive statement. And all of this is over 12. Alright, now remember what I said. We want it in its simplest form, so we don't want any like and unlike terms there multiple times. So if I look at my numerator, I have 4x minus 12 plus 3x plus 6. What I'm going to do is take all my terms with x and put them together. And then I'm going to put all my constants together, right? So when I put my terms in x together, I'm going to get a total of 7x. And look carefully how the integers come in here. We now have negative 12 plus 6. So if we remember correctly, negative 12 plus 6 will give us a sum of negative 6. Alright? And it's still going to be over 12 because we're still dealing with fractions. Now this is our answer. And some of the things I need to point out, because these are common mistakes, these are things that happen, these are things that happen to you in exam under pressure all the time. So if I had to simplify this statement, right? And noticing that I have a 6 here and I have a 12 here. Sometimes to students, they would think, well, okay, I have 6 and I have 12 and both of them have common factors, so I could cancel it down like this. No, you can't, right? That's a no-no. The reason why you can't do that, you have to remember you're dividing the entire statement, 7x minus 6, by 12. So if you want to cancel out a common factor, it must be common to both of them, right? And no, 6 is not common to both 7x and minus 6, so you can't cancel out a factor of 6 here, alright? So this is how we would treat with a statement like this.